Hi there. Hello. So we left off with you guys doing lesson 4 on your own, and I feel like based on the homework scores, that must have been like pretty straightforward, easy stuff. No need to rehash that. I want to do one Nearpod quiz just to make sure we've got something that we need to know, and then we're going to do lesson 5. Okay, so let's do Nearpod quiz. And actually, I'm going to do 2 Nearpod quiz questions, sorry. One over lesson 3 and one over lesson 4. So, if you could go there. Nearpod. While you're getting there, I should mention that the test has been pushed back to Friday. It was supposed to be tomorrow, but because of the snow day, we're going to need another day, so it'll be Friday.
I'm actually about to ask you that.
Yeah. That's right. Micaiah. Nope, it'll be due 7 a.m. Friday morning. I've already changed the deadline on it, so it's good to go. Thanks for asking. Extra credit due Friday morning. I almost said Saturday. Oh, Alyssa's not here. A pill, I'm fixing your attendance, don't freak out. I originally marked you absent, my bad. It's weird to talk to people through YouTube like that.
I feel like you can't see their face.
I know. So weird. Yeah.
Is Thursday and Friday, are those going to be like Google Meet days or for both days or?
Yeah. Or what?
Like what's the point?
So it should be Friday test, right? And so just show up to the Google Meet for attendance, and then we just go take the test. And then Thursday, there's a lab that we're supposed to do, so it'll probably be a very short Google Meet, and then you just go do the lab. Hopefully it makes sense. I'll be on the Google Meet the whole time if you have questions, but I won't hold you on there. That's the plan. Yeah.
There's like different for each class.
Is it?
Yeah.
What are they doing?
Well, some classes like we aren't having class because they're getting their
Appointment.
But most of my class, I think only one class we're not gonna like meet out on those days.
Mm.
Like just like make sure we have everything done.
Gotcha. That makes sense. All right, looks like I gave everybody enough time. I got all the answers here. Let's take a look at how you did. Look at that, 82% getting them correct. It was second order. Nice job. Okay, so how do we know it was second order? You're supposed to look at these graphs and find the straight line. I think the first two are curved, don't you? It's kind of hard to tell in the middle here, but this one is a straight line, and that's your inverse graph, so that's how I know it's second order. So just a quick review here. If you get a straight line on that inverse graph, it's second order. If it were on the natural log graph, it would be first order, and if it's concentration, it would be zero order. You have to have the slopes right, though. So in other words, this has to have a positive slope. So let me find an example here. There we go. If I'm looking at a graph like this, it is a straight line, but because it has the negative slope, this would not be second order, right? By the same token, If there's a curve, it is not second order, right? So real quick, let's see if you can tell me this. Maybe. What's the order of that graph? First order. If it was a positive slope here, it would not be first order, right? Okay, so hopefully that feels really, really easy to you. I'm going to help you with the memorization because in May, it's just kind of hard to keep all these facts in our head. So how are you supposed to remember that first order goes with natural log graph? If she came, yay! Toss it in the trash, Alyssa.
Okay.
If you remember, there's this reference sheet that has the equations on it. And I had told you there's a section called Kinetics, and it has these three equations right here. Okay, it has them in this order. So in other words, check this. The first equation on that reference sheet for kinetics is natural log, which happens to be first order. So that's how I remember that the natural log is first order, the inverse equation is second order, and I don't see any equation at all for just concentration, so that's how I remember it's zero order. It's on the paper 0 times. But I do want to remind you that there is sort of an equation for zero order that's not on that reference sheet, and it's that rate is equal to K. Because if that chemical A is zero order, that's the same as saying just rate is equal to K, right? So I need you to understand K is a constant. So what that's telling me is for this type of order reaction, the rate is constant. The rate is not changing. This reaction would not be slowing down over time, which is weird because most reactions do start out fast and get slower and slower and slower, but not if it's zero order because the speed of the reaction is a constant. Okay, so that's kind of something to realize, to keep in mind. Since we're on the topic of these equations, we said this one's first order. Well, this one is also first order, but it can be used to find the half-life. You can use this equation to find half-life also, but this is just kind of a shortcut to finding the half-life. Because you could put in an original concentration and then half of its concentration, and then the rate constant, you can calculate the half-life here. But this is just a quicker way to calculate it, easier. So only use this equation with the first order reaction, right? A couple other things to mention. This equation has the negative sign before K, and there is no negative sign before K in the inverse equation. And in both equations, the unit on time has to match the unit on K. And so a common trick on the AP exam is they give you the time in minutes and they give you K in inverse seconds. So if they're giving you K in inverse seconds, you have to convert the time that you're given into seconds to make sure that it matches. But that's the only curveballs that I can come up with, I think. So lesson 3 is okay. Remember when we were doing lesson 3 and we were using these equations, we were also using stoichiometry. So we want to remember if you're looking at a concentration and a rate in the middle of an experiment, then you usually want to do stoichiometry if it's in the middle of an experiment, just so you know. Okay, never mind, I've said too much. Let's try a lesson 4 quiz now just to make sure that everybody got what they needed to. So on Nearpod, there's a one question quiz here. Check all that apply for your answer. All right, looks like I got all the answers. There was just a couple of extra answers that people selected that they shouldn't have, but it looks like you all selected at least the minimum, which is good. Let's see what we should have selected. So the first three answers: collisions must occur frequently, they must occur in the right orientation, and they must have sufficient activation energy. They don't have to occur randomly in order to form products, but nobody chose that. They don't have to occur at the mole ratio. Guys, you can have an excess reactant, so they don't have to be in the mole ratio to still occur. They must result in forming an intermediate. No, sometimes they form intermediates. Actually, most of the time they form intermediates, but not always, so that's not critical for the reaction. And then they must occur under high temperature and low pressure. Actually, that would be bad, because under high pressure and low temperature, if you have a gas in your reaction, it's going to have intermolecular forces of attraction that actually cause some problems with the reaction itself, right? You may remember that vaguely from gas laws earlier in the year. So anyway, we just wanted these first three. So I wanted to show you this. Ew. Don't like seeing myself up there. So let's pretend that these are two reactants. In order to form products, they have to collide, right? So I'm just going to hit them together. They're going to collide. So when they do, occasionally it makes this really big sound, right? But sometimes they hit and absolutely nothing happens. So not every collision results in a reaction, because maybe they're not hitting at the right angle and the right orientation. Or maybe I'm not hitting them hard enough. Maybe they don't have enough energy to break their existing bonds to form the new bonds, right? Or maybe I'm just not hitting them frequently enough. If I only hit them once an hour, well, that's not going to result in very many products, right? So collisions don't result in products every single time. I have a reaction I want to try back here. I'm not sure it's going to show up great on camera, guys at home, but I'll do my best. I have two really big spheres that are kind of the same thing that I just showed you. I'm going to try to keep you off camera, Keegan. I don't know if I can do it. Feel free to move if that's not I've got two big spheres here. Basically, one of them is iron oxide rust, and one is aluminum. And when they hit together, they collide, they undergo the thermite reaction, which we actually saw outside, I think, earlier in the year. So anyway, I can get that thermite reaction to happen again if I can get the collision to occur correctly. But not every collision is going to result in that reaction taking place, right? So I'm only going to collide once, and we'll see if it works. We'll see. Okay, so hopefully this shows up on camera, but we'll collide them once, and we'll see if we're lucky. Ready? Can you see line left? Yeah, I'm not. Feel free to move. Sorry. Okay, let's see how good my aim is. Woo! Okay, but sometimes, you saw the big square? Sometimes this reaction doesn't do that. Sometimes when I throw the ball, I'll miss. Okay? And then if they don't collide frequently, it'll make the reaction. Or sometimes I don't throw it hard enough, or sometimes if the two brown parts, I don't know if you can see that on camera, if the two brown parts were to collide, they would hit at the wrong angle, and then that would result in a reaction, right? Okay, so we'll try one more time. It's fun. We'll try one more. See. Oh, see that one really, I don't know, there's a little spark, but not much, right? So every collision does not result in a reaction, good? They're just cannonballs. We soaked one in water to make it rusty and rust the other one in a little water. You got a good old cannonball. You can do this at home. Whew. Okay, so that's it for lesson 4. We're going to move on to lesson 5. We're ready to take some notes. Lesson 5 is going to be quick. We'll learn it today, and hopefully what I say today will be enough for you. Do a little practice in the homework, you'll be good to go. Okay, so lesson 5 is going to talk about something called mechanisms. A mechanism is basically like a theory for how reaction takes place. You see, this idea that a lot of collisions occur frequently in the right orientation with sufficient energy, that feels like that probably wouldn't happen very often. That's a lot of variables to have in the right place to make the reaction take place. So what we think is that the reaction takes place in several steps. Okay, so I want you to look at this picture that I have right here. Do you see how it says overall reaction and it lists this little guy? This is my reaction. So in order for this to happen and make this product over here, I got to have these guys colliding. How many molecules are going to have to collide? Two of these and one of these. Isn't that 3 molecules that have to collide in the right orientation with sufficient energy over and over and over again? I mean, what are the odds of that? It's slim, isn't it? So we don't think that that happens. We don't think 3 things collide like that. We think instead this reaction happens in 2 steps. Check this out. In the first step, just one of these NO2s reacts with an F2, and it makes some of the products. You see how we're supposed to make 2 of these FNO2s for the products? Well, it only makes 1 of them. Now, it also makes this F thing that gets used in the next step. We think that this F thing collides with the other NO2 molecule and forms my other product. So we actually think the reaction takes place like this. In step 1, we have 2 things colliding, and in step 2, we have 2 things colliding. One of the things that collides in step 2, we actually created in step 1. What do we call that guy? An intermediate. An intermediate, right? So an intermediate is something that's formed temporarily during the reaction. Why would it be formed during the reaction? Because we think that it's just part of the process of actually letting this reaction take place. We don't think that the reaction happens in 1 step. We think it takes several steps. So this is a mechanism, guys. A mechanism is just a list of steps that we think the reaction takes place in. Okay, do you see how this step is labeled slow, this step is labeled fast? Sometimes a mechanism will have 5 or 6 or 7 steps, but only one of them will be slow. And that step is the one we're looking for when we're working problems. So you want to kind of zero in on the slow step. Okay, so let's understand each step is called an elementary step. So this is elementary step 1, this is elementary step 2, and together they form this reaction, right? Each step has a different amount of activation energy. The one that's slow, that one's the one that's got more activation energy. That's why it's slow. So if I was to graph it, I know you guys saw graphs in the last lesson. If it has a 2-step mechanism, you're going to see 2 humps. If the first hump is taller, then there's more activation energy for this step. The first step would be the slow step here because it has higher activation energy. Well, what if my graph looked like this? There's still 2 steps, but it's the second step that has the higher activation energy. So in this case, the second step will be slow. There's always one slow step. How do you recognize it? Well, either they're going to label it as slow like this, or they're going to give you a graph and you just look for the tallest hump. That'll be your slowest step. Okay, so now we understand hopefully that some steps are called a mechanism and one of them will be slow. I want to show you why it's slow, or maybe kind of give you a visual to help us understand why it's slow. So I've got a set of funnels here to show you. try to position this so everybody can see. That might be about as good as it can get. Okay, so I've got a funnel here, a totally different size funnel here, totally different size funnel here, and then I've got a beaker at the bottom. So all I'm going to do is take some split peas and pour them through the funnel, so catch them in the beaker. All right, so we're watching this. Well, do you see how some are stuck in this funnel? Well, what that means is that this funnel is slowing down the process of transporting the peas, right? So if the peas are reactants up here, and they're converting into products, they're going to go through several steps to convert into products, but only one of those steps will be the slowest of all the steps. And that step, in this case, happens to be this biggest funnel right here, right? Okay, so I would say this is an elementary step, this is an elementary step, this is an elementary step. This one is my slowest step, so that's an important step because it is determining the speed of this whole thing, right? We call the slow step the rate determining step because it's determining how fast this thing goes. Okay, so the slow step is very, very important, and there will always be a slow step. You just got to figure out which one's the slowest. Hopefully we can do that. So let me go back to the PowerPoint for a second. Okay, this last little detail is really important. The steps must add up to the overall reaction. Okay, so these two steps have to combine to make this overall reaction. Do you remember a long time ago, we were taking equations and we were combining them, and if something showed up as a reactant and as a product, it canceled? And if two things showed up as reactants, they combined. If two products showed up, they combined, right? So in order for this mechanism to make sense, it has to equal the overall reaction. So we're just going to look at, oh gosh. Trying to decide. Yeah, let's skip some stuff here and let's look at this practice problem here real quick. Ignore all the words. Do you see how it says step 1, step 2, step 3? This is a mechanism. Let's go ahead and combine all these into an overall equation. So I'm going to actually need to copy these on the board, I think, to make it make sense to you. Let me do that real fast. Hang tight, please. Always worried I'm going to copy something wrong and then make it confusing. Don't let me do that. If you see me copy something wrong, yell at me. Okay. Whew. So step 1, step 2, step 3, right? We're going to combine all these into an overall reaction. What can I cancel? H2Cl. Perfect. So this guy cancels this guy. What else can I cancel? OH minus and OH minus. N2H5 plus, N2H5 plus. Anything else? No. So this reactant and this reactant should be combined together into 2NH3, right? And then I've got another little reactant hiding here, OCl minus. Looks like I got 3 products, N2H4, a Cl minus, and a water. Now you could change the order of these products, you can change the order of these reactants, but this is your reaction, right? Is that okay? Basically, a mechanism has to make sense. It has to equal this overall reaction. Okay, sorry, I'm going to go back now. Yeah. Okay. If you look at each individual step in a mechanism, you can label it as a unimolecular, bimolecular, or termolecular. It's just a vocabulary word that we're going to need to use. So if you look at this step, you see how it has one reactant? That's unimolecular. Okay, well this one has two reactants. Yes, it's the same reactant, but there's two of them, so that's bimolecular. If they were different, it would still be bimolecular. 3 or more reactants is going to be termolecular. Whether I've got 3 separate different molecules or 2 molecules of one kind, one of another kind, this is still termolecular. So is that okay? That's pretty easy stuff, just like basic vocabulary right there. Okay, so now we're going to get into the real purpose of a mechanism. Why do we have mechanisms? First of all, a mechanism is used to explain how a reaction takes place, but it's also used to get us the rate law. Guys, you can get the rate law from the slow step because it is the rate determining step. You know how you do it? The coefficients in the slow step, those will be your exponents. You know, this whole chapter we worked really, really hard to figure out those exponents, right? And now I'm telling you, if you have a mechanism, just go to the slow step and its reactants will be in your rate law and its exponents will be your coefficients. I mean, this couldn't be easier. You're just looking at the coefficients. Now be careful. Sometimes the slow step will have an intermediate in it. And that's bad because it says intermediates cannot be in the rate law. They will have to be replaced with something. So you have to recognize an intermediate and then replace it. And some people will confuse an intermediate with a catalyst. So let me try to help you understand the difference here. An intermediate will be produced in one step, and then it'll be a reactant consumed in a later step. Now, a catalyst is different because it's going to be present at the very beginning and the very end of the reaction. Because remember, catalysts don't get used up in the reaction. So it's going to appear in the mechanism at the very, very beginning and the very, very end. Like very, very beginning, very, very end. And that's different from an intermediate. So let's go back to this one. Let's look at this chemical here. Can you tell me, is that a catalyst or an intermediate? Intermediate. It was created in step 1 and then it gets used in step 2. OH was created in step 1 and used in step 3. That's still going to be an intermediate. So there can be like a bunch of steps in between where it's produced and where it's used. It's still an intermediate. A catalyst would be something that appeared here and here at the very beginning and the very end. So the point is, you're supposed to pick the slow step, go straight to whichever one's the slow step, and you're going to write your rate law. When you write your rate law, you use the reactants that are in that slow step, and their coefficients will be your exponents. The problem is, if your slow step has an intermediate in it, then we have to fix that. So we're going to go through examples of how to fix that. Okay, so we're back to this practice problem. We already figured out the overall stoichiometric equation, right? We did that. Okay, can you tell me which step is the rate determining step? Step 2. Okay, so then let's write the rate law. If it's step 2, we're just going to go straight to step 2 and write these reactants with their coefficients as exponents. Okay, so let's do that. You said it was step 2. So these are my 2 reactants, right? NH2Cl, NH3. Let's raise them both to a power of 1 because they both have a coefficient of 1. Now there's a problem with this rate law. If we leave it like this, what's the problem? Yeah, it's got an intermediate in it. So you're not allowed to have the intermediate in it. Okay, so why? This is important. Why can't you have an intermediate in it? Well, isn't this my overall reaction? Shouldn't its rate law be something like rate equals K times this chemical and this chemical raised to some power? Well, the intermediate is not in the reactants of the overall reaction, so it doesn't make sense to have it in the rate law. Right? We're trying to find the rate law for the overall reaction. We're getting it from the second step of this mechanism, but that guy's got an intermediate in it, and that didn't make sense for this guy's rate law. Okay, so we got to do something about that. What do? Well, you're going to replace it. You are not just going to delete it. You are going to replace it. What do you replace it with? The chemicals that made it. So what chemicals made this guy? These chemicals, right? These reactants. So both of these reactants created that guy, and that means they are going to take his place. And they both have coefficients of 1, so both of these chemicals will just be raised to the power of 1. Let me write it like this. Rate equals K NH3 raised to the power of 1, OCl minus raised to the power of 1, and we still have this NH3 raised to the power of 1 on the end here. We're not getting rid of that. So this portion here is just replacing my intermediate. And I'm sure people at home can't even see that very well. This portion here is replacing my intermediate. We're getting rid of that, replacing it, but you're not getting rid of the other chemical NH3. Do you follow what I've done with the intermediate? Okay, so what do I got to do to finish this? Yeah, you're just going to combine those two NH3s so they're not separate, because that's weird, right? Would it be NH3 to the second power and OCl minus to the first power? There's my rate law. There we go. There's my rate law. Okay, so recap. How can we get a rate law? Well, you can do a bunch of experiments and get you a data table together, figure out the rate law from the data table. Or you can do the experiment one time and you can make a graph for each of these two chemicals, and the graphs will tell you if it's second or first order. Or you can get a mechanism. If you have a mechanism, all you need is the slow step and you can write the rate law. And I think that's maybe the easiest way to do it, but there are 3 ways to get the rate law officially. And I know we've said this before, but it's worth saying again. What are the intermediates that are involved? There were 3 different intermediates. This time are the things that we canceled out. Don't confuse those with catalysts. Doing good? Huh? OH minus was an intermediate. Is it not listed? Or you're answering the question? No, you're good. You're answering the question. So we have actually 3 different intermediates. You're right, Olivia. OH minus is one of them. But yeah, there were 3. Okay, so we're just going to try to see if we can wrap our minds around mechanisms a little bit more. I think we're kind of starting down that road. Okay. All right, check this one out. Guys, this is a mechanism, step 1, step 2. Can you just identify a catalyst? V2O5. Awesome. V2O5 is a catalyst. So how do you know that? Because it was present at the beginning and also present at the end. Well, then what's V2O4? It's an intermediate. How's that different from a catalyst? It was created and then later used. It's a reactant first, then a product. Could you combine these into an overall reaction? We would cancel the V2O4s. We would cancel the V2O5s. You would just have SO2 plus half an oxygen makes SO3. Now, they will usually tell you which step is slow, and that will be the one that you go to get your rate law. If you are not told what step is slow, then they're giving you the rate law, and we can figure out which step is slow from that. So we're going to look at both situations. Before I go further, I forgot to say something here. Our rate law is kind of muddy here. I'm trying to clean it up. I want you to look back at this rate law here and how it related to this overall reaction. Weren't these our reactants? Didn't those end up being the chemicals in the rate law? Okay, now be careful about this. the exponents here happen to match the coefficients here. But that's a coincidence. So you never want to take an overall equation and just go, oh, those are my coefficients, let's make them exponents. No, you can only do that with a slow step. If you have a single elementary step in a mechanism and you know that's slow, then those coefficients become your exponents. But for an overall reaction, it doesn't work that way. So it just happens to be that those match these coefficients. Now, there's one situation in which you can't. If they tell you this reaction happens in one step, if it happens in one step, doesn't that one step have to be the slow step? And then that would mean that you could use these coefficients as exponents, but they have to explicitly say this reaction happens in one step. If they don't just lift those coefficients and make them exponents, you'll get it wrong. Okay, I hope that was okay. Let's do another problem. All right, here's my overall reaction. They think it happens in 2 steps. A fast step and a slow step, right? Let's write a rate law for this reaction. So you're going to go straight to your slow step, and you're going to write the reactants and raise them to the power of their coefficients. Sorry, I thought I had some more helpful things typed on here. I don't. Let me erase more of these. Thank God for good erasers. Ugh. Couldn't even imagine. Okay, so I'm going to go to slow step, and I'm literally going to do this. Rate equals K times that first reactant raised to the first power because it has a coefficient of 1, times the concentration of the second reactant also raised to the first power because it also has a coefficient of 1. Okay, now, don't just stop there. Ask yourself, does this thing have an intermediate? Yeah, and that's in this rate law that I just wrote, right? You're not allowed to have that. So what am I going to do? I'm going to replace it. So the rate law would look like this. What would I replace it with? NO, and that thing has to be raised to the second power because it has a coefficient of 1, right? Now I'm not going to delete the O2. That's going to stay in the rate law. So now, last thing I do is ask myself, does this rate law make sense with the overall reaction? So I go to the overall reaction here. It's got NO and O2 as reactants. Well, NO and O2 are in my rate law, so that part's good. But don't assume that the coefficients in that overall reaction are going to be your exponents. If it is your exponents, it is a coincidence.
That the elements in the rate law are the same as the reactants in the overall.
No, so that should definitely be true.
Okay.
The only possibility is, like this might not be there. At least in your rate law, these things have to appear in the overall reaction as reactants, but maybe not all of the reactants would be in your rate law.
Okay.
But what is there must appear as a reactant.
Okay.
Yeah. Good question, Alyssa? The coefficient in this step right here. Yeah, so when I found NO2 as an intermediate, I looked to see what created it, and that chemical gets raised to its coefficient power. So it has nothing to do with this little 2 down here, though, right? It's like terrible examples. I don't know how to deal with that. Let's look at another one and see if it makes sense. Sorry, Micaiah. Yeah. No. Never. So this 2 had an exponent on the NH3, right? But that is total coincidence that it matched the exponent of this overall reaction. It's coming from the fact that NH3 appeared here to the first power, and then it also appeared here to the first power. So you want to take your slow step, look at its coefficients, and then if it has an intermediate, it might get replaced with something else that could then combine to increase your exponent. That's what happened there. So in other words, this is originally what I had as my rate law. But the problem is NH2Cl was an intermediate. So I replaced it with this part. See the NH3 and the OCl minus? But now I just combined those two NH3s to give me my square. But that's total coincidence that it matches the coefficient in the overall reaction. Yes. Yep. If there was another step with the NO in there. Let's look at another problem. This might help you too. This might make sense. And we have more to do tomorrow. We are going to do a lab, but there's going to be some practice problems involved also. Okay, so hang on. Guys, it tells me that this is a first order reaction. Do you see how this overall reaction has a coefficient of 2, but yet it's a first order reaction? Okay, so let me try to make sense of that. What that tells me is that my rate law is going to look like this. Rate is equal to K, and then NOCl will be raised to the first power, even though it has a coefficient of 2. It's first order. Okay, so we want to write a mechanism that explains this. And it says to use 2 steps, one fast, one slow step. Okay, so in my first step, I'm going to take a single NOCl because 2 NOCls, if they were to both collide, this would happen in one step, right? So it must be that I am only starting with a single NOCl. Now, what am I going to do with that? I'm going to decompose it. Isn't this decomposition? I'm going to break it. I'm going to break it into NO and Cl. Well, why did I do that? Because I'm trying to make these products, so I decided to make one of these NOs. Okay, do you see Cl in this reaction here? If Cl is not in the reaction by itself, not Cl2, that's not the same. This is just Cl. That's not here, is it? Doesn't that mean this is an intermediate? It's going to have to disappear. It can't be in the overall reaction. So if it's an intermediate, I'm going to use it in my next step. What am I mixing it with? The other NOCl. You see how the overall reaction needed 2 NOCls? Well, the second one is getting used in the second step with the intermediate. And what are they going to make? Well, look at the products that I have to have. I have to have a second NO, don't I? And I have to have a Cl2. So the products is going to be that second NO and the Cl2. Just look at that for a second and see if that makes sense. If these are my 2 steps, wouldn't they combine to equal this? Okay, they won't ask you to write a mechanism on the AP exam, but I'm hoping that by doing this, you're understanding that these 2 steps must combine to make this. Now, wait a minute, can you figure out which one's the slow step? Remember, it told you that this thing's first order. So in other words, it's telling you that the rate law has to have an exponent of 1 on the NOCl. What that means is that this step has to be the slow step. This chemical will be raised to its coefficient of 1. Well, what if this was the slow step? Well, then you'd have an intermediate that you'd have to replace with this. So you'd have this chemical raised to the first power, and then you'd be replacing the Cl with this chemical also raised to the first power, which would make it to the second power. So that's how I know that the slow step must be the first step. One more time, the exponent is the coefficient of the slow step, not the coefficient of the overall reaction. I'm sorry I ran over. Thanks for tolerating me. I'll try to do more practice tomorrow on the Google Meet. Don't forget.